Hi everyone. Today I'm going to give an introduction to the Scanning Electron Microscope lab, where we'll use an electron microscope to verify Moseley's law, that is to look at X-ray emission from different elements and see that they can be described by a simple law. I'd like to start by going over some theory, and then we'll take a look at the electron microscope. Okay, it helps to contrast an electron microscope, like our scanning electron microscope, with an optical microscope. In an optical microscope, light from a source is collected onto a sample, and then light that's transmitted through the sample is re-imaged onto a camera through a set of lenses. In an electron microscope, a beam of electrons is created. These are emitted from a hot cathode, basically a hot filament, and they're accelerated across a high electric field to create an energetic electron beam. This beam is focused with electric and magnetic lenses, and then it's focused onto a sample. In a scanning electron microscope, the following happens. When the electron beam hits the sample, some electrons are scattered off. These are called secondary electrons or backscattered electrons. And we measure the current of those electrons, and then we use magnetic fields to scan the electron beam around on the sample and watch how the current changes with position. Actually, we raster scan the beam across the sample to build up an image of the sample. Okay? So the scanning beam is why this is called a scanning electron microscope. Here's a cartoon picture of the electron microscope like the one that we're using. In our electron microscope, there's a cathode with and electrons are emitted from the cathode. It's actually a hot filament. They're accelerated across a voltage. We may be using a voltage of 15,000 volts, for example. This shows the electromagnetic lenses, and the beam is focused onto the specimen or sample. An additional magnetic component is used to steer the beam around on the sample. Something I didn't mention, but in order for this to work, the electron column and the electron beam have to be evacuated. There can't be any air in here. Otherwise, the electrons would just scatter off of air molecules. So electron microscopy is normally done in a high vacuum. Okay? Once the electrons hit the sample, some electrons are scattered off in all directions. These are called secondary electrons or backscattered electrons. And then we have an electrode over here, or at some place, which captures some of those electrons. And we measure the current of electrons as the beam is raster scanned across the sample, just as I mentioned before. And in doing so, we can build up an image, like this lovely image here of an ant head. Wouldn't you want to wake up with that next to you in bed in the morning? The electron microscope itself is a small, relatively small instrument which can fit on a relatively small tabletop. This is the same model of microscope that we're using. In fact, most of the space is underneath this, and it's just the vacuum pumps necessary to pump all the air out of the electron microscope. It's useful to look at what happens when the beam strikes the sample, okay? So when the electron beam strikes the sample, several things happen. Electrons near, in the vicinity of this point can be scattered off. Those are called secondary electrons. The incident electrons penetrate some distance into the sample, and electrons can be, from the beam, can be backscattered at any point. Those are the backscattered electrons. But interestingly also, any of the atoms here that are excited by the beam of electrons may relax by emitting X-rays. And so X-rays will be emitted from a somewhat larger volume that's being excited by the sample. So while the sample beam spot might have a characteristic size of only a few dozen nanometers, the size of the spot that's emitting X-rays might be 1 micron or something like that. Situated above the sample in the scanning electron microscope, we have electrodes to collect secondary or backscattered electrons. But typically, we also have a path for some of these X-rays to travel along, which will lead them to an X-ray detector. And in the X-ray detector, we measure their energy, okay? So we can measure the X-ray spectrum. All right. So what do we expect to see in the X-ray spectrum? Well, to figure that out, we can look at a simple shell model for our multi-electron atom, like an atom that we might be exciting with our system. The high energy incident electrons can knock electrons out of the atom. So they might knock electrons out of the K shell or the N equals 1 or innermost shell of the atom. So now my kicked off electron goes somewhere else. It's a secondary electron, in fact. But once that's happened, we're left with an unoccupied state in the N equals 1 orbital. And another electron in the atom will typically fall down to fill that unoccupied state because it can reduce the energy that way. And often when that takes place, the excess energy is emitted as a photon. In heavy atoms, these energy differences are large, and so the energy of the photon is large as well. And these are X-rays that are emitted. X-rays that are emitted when when electrons drop from the N equals 2 or L shell to the N equals 1 or K shell are called K alpha X-rays. Those from N equals 3 to N equals 1 are called K beta, and so on. If an electron falls from the N equals 3 to N equals 2 shells, that's an L X-ray, and this one would be L alpha X-ray, okay? Our analysis is mainly going to focus on the K alpha X-rays because they're the simplest to describe. But we'll also talk about K beta X-rays, those that go from N equals 3 to N equals 1. Here's the idea. Even though multi-electron atoms are actually rather complicated, their basic features are simple enough that we can understand them with just a hydrogenic model. In particular, the electrons in the K shell, the innermost shell, they feel somewhat like electrons in a hydrogen atom. That is, they're both orbiting a nucleus. They don't see the electric field due to the outer electrons because they're inside of those shells. And so it's kind of like a hydrogen atom. Only there are two differences. The most important difference is that the charge of the nucleus isn't 1, but it's Z, okay, where that's the atomic number of the atom. The second thing is that this atom, if you like, contains another negative charge, the other electron in the K shell. And that makes the effective charge of the nucleus smaller. It reduces it by about 1 because we have 1 electron charge here, okay? But otherwise, it's pretty much hydrogenic. So we would expect that we can predict the energy of a K alpha X-ray from our theory for the hydrogen atom with a few small tweaks, okay? All right. Well, that treatment leads us to Moseley's law, which you can read about in our textbook and also in the paper by Conover and Dudek. But the result is that the energy of the X-ray, of the K alpha X-ray, should be a constant times Z minus sigma squared, where Z is the atomic number and sigma is the screening parameter. It's the reduction in the effective charge on the nucleus because you have this other electron in the that the first electron can interact with as well. In the simplest possible model, B here would just be 3/4 of the binding energy of the hydrogen atom, because that's the energy for the N equals 2 to N equals 1 transition in a hydrogen atom. And then, since we know we have an expression for the binding energy of the hydrogen atom, we can rewrite this term here in terms of fundamental constants. Also, in the simplest theory, sigma, the screening parameter, would just be 1. Real multi-electron atoms are somewhat complicated, so we might expect that the screening parameter won't be exactly 1, and perhaps we'll get a slightly different number for B as well. But if Moseley's law is valid, at least we expect this form to describe our data, where B and sigma might be arbitrary constants that we use to fit our data. But once we do the fit, we do kind of expect that B will be equal to this, and that sigma will be a number on the order of 1. Okay? That's the theory. By the way, well, actually, I'm going to explain that to you. I have a point, but I'll explain it to you when we're looking at the microscope. Let's stop here for the moment.